Kuldeep.
And I'm Peter.
This is the Root Motive Podcast.
All opinions expressed are those of the hosts and do not necessarily reflect the position of any other organizations or affiliations.
Hey guys, welcome back to the episode 5 of the Root Motive Podcast. I'm Peter, and as always with Kuldeep. And today we have our second guest, Jay, who's a friend of Kuldeep's, lifelong friend, or from early on in Kuldeep's life. So I'll let him do some more background introduction later, but he's going to be here talking to us today about astronomy topics, and he's currently a associate or a research fellow at the Maria Mitchell Association in Nantucket, and he's a recent graduate last year of Vassar College in Poughkeepsie. And so we're excited to have him on, and I'll let Jay do a little bit more background introduction.
Cool. I've actually known Kuldeep since the second grade. We actually didn't get along very well way back then, but since high school, we've got Kuldeep's been like a brother to me. So really excited to be on, guys. Thanks for having me.
So Jay, why don't you introduce yourself to the audience?
Sure. As Peter said, I work as the research fellow here at the Maria Mitchell Association. It's sort of a postgraduate position for sort of as a pre-graduate school bridge program. So I'm studying astronomy here for the year, and next year I'll be going to CU Boulder to hopefully get a PhD in astronomy. In my downtime, right now I live, as I said, at the Maria Mitchell Association. I live on Nantucket Island, which is a really beautiful place. And so I've spent a lot of time outdoors the past few months, more so than I think I have even living where we did previously. So I do a lot of outsider stuff, especially in quarantine now. I've also been playing a lot of more video games. Science fiction is something I'm really into, sort of what brought me into, I think, astronomy in general. Yeah, that's a little bit about me.
All right, thanks, Jay, for that introduction. Why don't you also go into some background about kind of the research you've done in college to date, and then kind of where you're headed in terms of your work aspirations?
Sure. And actually, let me start a little bit before college. I had originally went to college thinking I was going to study politics, and I think Peter and Kuldeep know that about me. And at the end of my first year, I took a class in astronomy. It was sort of an intro class, 200 kids. It was sort of a throwaway, but I really, really liked it, and it really brought me back to that thinking about science fiction and thinking about the universe, and it was really awesome. And in the following fall, so in my second year, my professor convinced me to go along on a trip to a research symposium where some of my classmates in astronomy were presenting their research. And it was really, really awesome. I was sort of blown away at some of the research on galaxies, on planets, and all these amazing things in astronomy that they were able to do just as undergraduates. And I think it was at that moment that I sort of like did a 180 and decided to study astronomy instead of politics. As an undergraduate, I worked at an observatory on campus. I also did a senior thesis on something called a protoplanetary disk. That's the disk of material around a star that eventually forms planets like we have in our own solar system. And right now, what I research is something completely different. I look at galaxies far away, studying something called fast radio bursts. You all might have heard about this in the news. Mm-hmm. I'm not so interested in the fast radio burst as what other science were able to do using them sort of as flashlights through the universe. That's sort of what I do right now.
Interesting.
Watch that video that your presentation with one of your instructors, and you were talking about, I think, the source of it, or the source of fast radio bursts is still kind of like there are several possibilities, but it's not really clear necessarily from one fast radio burst what the source is. So I don't know. I found that kind of interesting. Like, do you want to maybe go into depth a little bit more about what actually the different types of fast radio bursts can be sourced from?
Yeah, that's a really good question. And I actually have some really exciting news to share that you might have noticed out in the news, especially in the past few weeks. So since I gave that talk, I gave a science pub talk here on the island about some of the research that I do. So these fast radio bursts, just to give your audience a little bit of familiarity in case they don't know, they're millisecond time scale events, which means that's like 1,000th of a second. It's hard for us to perceive that. And we detect them these radio bursts in, again, the radio regime. So radio is a kind of light. It's not just, I remember when I was young, and especially before I had taken physics classes, I really didn't realize that things like radio and X-rays, those are all kinds of light. And so we detect these fast radio bursts coming from other galaxies. And if we are detecting them from other galaxies, that means they're like super bright. For example, a single fast radio burst can give out the same amount of energy that our sun does in a single day. Very, very powerful events. And we detect them very frequently. In fact, we think that there's a fast radio burst happening probably once every 10 seconds or even more often than that. It's harder to detect all the time. But we believe this telescope called the Canadian Hydrogen Intensity Mapping Experiment. It's called CHIME for short. Astronomers love their acronyms. Since it's gone online searching for fast radio bursts, I believe it's detected over 100 fast radio bursts within the last year or so, which is really exciting. We don't fully know, let me caveat that, until about 2 weeks ago, there were about 50 different theories about what fast radio bursts could be. A lot of them have to do with the cataclysmic end stages of giant stars. So we know stars like our sun, in 4 or 5 billion years, it's going to turn into something called a white dwarf. It's going to shed the outer layers, it's going to expand, and what's going to be left over is going to be this really hot white core of the sun. Instead, other more massive stars, so stars bigger than our sun, something like 4 times or bigger, they go black. They become black holes. They become something called neutron stars, which is the magnetic core that's sort of the remnant of the star that's gone supernova. There's many different cataclysmic events that we thought, in combinations of them, like a black hole colliding with a neutron star, black holes colliding with each other. We thought these kinds of energetic events could explain something like fast radio bursts. They have this sort of energy output that could explain something like a fast radio burst. And we even right now, we think that there's multiple objects that can create those fast radio bursts, as you were saying, Peter. And really, it's going to take time for us to understand all these avenues of possible progenitors, as we call these objects that could create fast radio bursts. These possible progenitors of FRBs. That's the acronym for fast radio bursts. Until about 2 weeks ago, it was really exciting. On April 28th, CHIME, that's the Canadian, that array of radio dishes that detects fast radio bursts, detected a fast radio burst in our own galaxy at an object called, let me just refresh my memory real quick. It's called SGR 1935 plus 2154. Some long, boring astronomy number. It's an object that we know in our own galaxy is something called a magnetar. It's a neutron star that's, again, one of those end stages of a star's life that's possible if it's really, really big. A magnetar is a really energetic, like something like a billion or trillion times more magnetic than the magnetic field around our own planet. So this really magnetic remnant of an old star, something like 40 or 50 or so, even bigger than that, possibly, mass of our own sun. And we detected an FRB coming from that object within our own galaxy. And that's a really exciting, it's sort of a breakthrough, really, and almost confirmation that this kind of object, this magnetar, is a source of fast radio bursts in other galaxies far away. So the mystery...
Damn, dude, that's hype.
Yeah, it was super hype. I mean, I remember when I got the notification in one of my work class. Craft is an experiment on a similar telescope array to CHIME in Australia. So I work with Craft more than we really don't work with CHIME, the people in our collaboration. We all lost our minds. We're running through the internet. We're like, can we get a telescope pointed at that object? Who do we have to call? What do we have to do to find out, get more data on this? It was a really, really exciting moment when we read the report.
2 things. First of all, it sounds like a Pokemon. Second of all, this is recorded on May 10th, just for reference, in case anything comes up in the future between when this is recorded and released that contradicts what we talk about today.
Yeah. Wait, so is there any difference in the fact of how close that fast radio burst was emanating from? Could there be more, I guess it wouldn't really matter. Could it affect us in some way? Like, do you know of any of how these might?
That's a good question. So the good thing is, to my knowledge, radio light, especially the kinds that we're talking about, even though it's super energetic, even if it's coming within our own galaxy, we're probably going to be okay. The real trouble is if there's a magnetar close by, or there's other theories about fast radio bursts. Some of them involve other very energetic end stages of lives of stars, like the actual event called a supernova when an old star explodes. If that ever happened near us, that would be very catastrophic to human life. Specifically, something called gamma radiation. The more energetic the kind of light that an object emits, the more dangerous it is to human life. For example, X-rays are nominally harmful to us. They're also helpful to us in detecting things like we use them in medical equipment to diagnose diseases and look through look inside of us. I'm sure many of us have had X-rays before, but you might know that you don't want to get X-rays all the time because, again, that's partly harmful radiation. Gamma rays, there's another phenomena in space called gamma ray bursts, opposite of fast radio bursts. You can think, if not opposite, actually, they might actually be related, to be determined.
Yeah.
That would be very deadly if something like a gamma ray burst happened near our wonderful home.
Can I just ask a quick question? You said black holes colliding with black holes. What is that about?
So this is sort of an almost a known effect. I don't want to say 100% known. You might have heard of something called gravitational waves. This is another astronomical phenomenon that is also a humongous game changer for astronomy in general. Mm-hmm. When massive objects in our universe collide, when something crazy or interesting happens to them, they release gravitational waves based on their masses. That's sort of an offshoot. It's a predicted event from Einstein's theory of general relativity. But black holes can collide, and we think we've detected black holes colliding. Actually, I might want to double check myself on that. But we can detect them through gravitational waves. So if you imagine that there's a giant star, we know that there's 100 billion stars in our own, over 100 billion stars in our own galaxy. If a star is massive enough, it can become a black hole. Then you can imagine there's a probability, it's a small probability, that if star A goes supernova and it becomes a black hole, and there's a sort of nearby star that also happens to become a black hole, because of influences of gravity, because of motions within a galaxy, they might get closer and closer, so close that they spin around, and they get closer and closer and closer, and they finally become one object. Probably one of the most energetic events we can imagine that happens in the modern day universe would be black holes colliding.
Interesting.
Yeah, that sounds pretty intimidating.
It would be. You would not survive if you were near that event. I can't imagine anything that would.
Yeah.
If it happened in our galaxy, would we survive?
I think so. In fact, there's some...
How big is our galaxy?
Our galaxy's enormous. I'm actually...
Compared to the size of a black hole or two black holes colliding, like what percent of space is that? Like, is it an ant in a stadium, or is it like a football in a stadium? Like, how big is it compared to the galaxy?
So that's a good question. And I'm actually gonna do this popular astronomy technique that we learned in Outreach, where I divert the question and I explain something else interesting to you. So I don't fully know. I'll settle for that. So these objects, when they have to spin in, there's probably a long, huge distance between them before they start spiraling in because of gravity. And the distance between them could be huge. It could be light years. In time, they'll get closer and closer, and then they'll collide. But you might remember last year, there was just a year and a couple days now ago that we had the first picture of a black hole. Scientists both at MIT and around the world, it was a global effort from the Event Horizon Telescope to take the first images of a black hole. And one of them was the image of the black hole at the center of our galaxy, Sagittarius A star. And as you might recall, and there's also another one from another distant galaxy that we were looking at. If you imagine that picture in your head, I know some of your audience can Google a picture of a black hole. There's this really bright area around a dark black circle where there's no light. And then there's light around that circle. The part that's in the circle, that's defined by this limit around the black hole where light cannot escape. It's called the event horizon. So the size of that dark region where we cannot see anything is bigger than our entire solar system. So you can think of the black hole as that event horizon sized object. That thing is bigger than our entire solar system, just to give you a size of the scale. And that was a supermassive black hole. So the most massive objects in our modern day universe, these single objects, these supermassive black holes, can be bigger than the size of our whole solar system. But even that is really, really small in comparison to even the size of a galaxy. Galaxies are thousands, tens of thousands, even 100,000 light years across. And the nearest star, just to give you an example, the nearest star to us is something like 4 or 5 light years. So that's smaller than the size of this supermassive black hole. So space is big. Things are very, very spread apart. But when things are big, they're enormous.
Yeah.
Gotcha.
Yeah, I kind of wanted to get into exoplanets, I guess. Cool. Do you have any more questions?
I don't know. When he said black holes colliding with black holes, it didn't make any sense to me because, like, how can a void collide with a void and then produce radio? But I guess that makes sense. We don't really understand black holes anyways. So it was kind of a dumb question on my part.
No, it's not. There's no dumb question. I think it's a really good question.
Yeah. Thank you, Jay, for validating my feelings.
That's sort of what the cool thing is. Can you imagine what other, I don't know what other field you can just shoot out a question and be like, hey, Cooley, what's going to happen if two black holes collide? And that's really something we're trying to find out. That's a real serious question that astronomers are thinking about. Like, really, what does happen when two black holes collide? It's really one of the cool things I'd like to think about.
All right, yeah, we can move to exoplanets. That was my own question.
Yeah, so like I was looking into it a little bit and just looking at like how they've basically been like within the last decade. It seems like the exoplanet finding once Kepler, I think, was launched.
Mm-hmm.
That was when like it started to take off, and so there's been like 4,000 exoplanets discovered in our galaxy alone, and a lot of them I know are easier to detect the closer they are because I know they're small technically relative to stars, so they're like they use spectroscopic techniques to identify the presence of the planets. So I just thought it was interesting because obviously looking to go to Mars, we're trying to look for habitable planets, and obviously it's always an interesting topic. So I thought it would be cool to like maybe break down like what your thoughts are on like the probability of there being like exoplanets that are actually suitable for life and that have like the Goldilocks conditions and like the probability of that maybe based on like some of your just reading, I guess, or some of your work if that ties in.
It's actually an ongoing question, Peter, but it's probably one of the most important questions that astronomy can ask, especially right now. As you mentioned, we have one beautiful habitable planet within our own solar system. And everything else, even just within our own solar system, is absolutely not habitable to human life. Mars, we can make it by. It would be as awful as living in a volcano on Earth. It would not be the prospect of living on Mars. We should not. This is a political statement, but I'm always hesitant to glorify the idea of living on Mars. Y'all, it's going to be terrible if you have to live on Mars. It's going to be a dull and dreary life, and yet we're thinking about it. And I think it's worth thinking about. It's a good question, and I really like that. But it's an ongoing question as to what the probability of habitable planets are, even within our own galaxy, let alone other galaxies. Let me break down.
I would argue, though, I mean, that is your stance as an astronomer. That makes sense. But as an engineer, I would argue that we need to first figure out how we can make humans live in a habitat on another planet before we can even think about going to any other planet. Right. So like we need to figure out how we would live on Mars for at least a couple of years before we can even think about going beyond the reaches of our solar system.
I totally agree.
It is a worthwhile effort, but not the end goal to like permanently live on Mars.
I don't know. I just think like the properties of Earth are going to be so unique, like geomagnetically. Like I feel like there's so many variables that go into play. Like we need to save Earth. I've always found that, and Cooley and I were talking about this at some point, so I just wanted to hear because like Elon Musk and a lot of people are making kind of popularize this concept of like space exploring and going like being a pioneer and going to Mars. But I feel like we need to just save our planet, and it's much better to stay here. So yeah, thank you.
That's actually something I always think about as an astronomer. Because in the back of my mind, I always thought, like, especially because I'm hoping to do research on exoplanets in the future. That's sort of what I wanted to go into. At the same time, there's this idea in the back of my head. I'm like, well, I kind of hope we find another planet out there. But every other fact around me is saying, don't think about that, because we're never going to be able to get there. Not within my lifetime, not within, generations. It's an idea that's hundreds of, if not maybe even thousands of years off. Mm-hmm. So you're right. We have to think about saving our own planet before we can think about colonizing Mars. Or saving our own planet is easier than colonizing Mars right now, and it probably will be for a long time.
Very true. Yeah. Very true.
I'll give you a real quick awesome thing about that. I like to think about in exoplanets. So you're right. We only have detected thousands of 4,000 or so exoplanets in the last 10, 15 years or so. In the 1990s, people didn't even believe exoplanets were real. People didn't even think there was real doubt in astronomy whether there were planets outside of our solar system, until multiple people detected exoplanets using something called a transit method. That's basically the light around a star will dim a little bit because there's a planet passing in front of the star relative to our line of sight. And because of that awesome sort of simple technique, we've detected now 4,000 exoplanets, most of them with that method. There's the Kepler Space Telescope that detected a lot of them, and now we have TESS, the Transiting Exoplanet Survey Satellite. That's up in space right now, and that's looking across the entire sky looking for exoplanets. It's finding them right now as we speak. And the field has really evolved. So first it was about detecting exoplanets. We found a problem, though, is that we were finding all these things called hot Jupiters. It's because the technique that we use to find these exoplanets have a bias. It's easier to find large planets that are really close to their parent stars, because we're going to see a decrease in light more easily in those scenarios than an Earth-sized planet around an Earth-sized or a sun-like star at a distance of the same distance that we have between us and Earth. That'd be like we've only found very, very few. I think within one hand, I can count off the number of exoplanets that would match that description. And it's hard. It's because of the limitations of our technology. We're trying to build new techniques, new telescopes. One of them is James Webb, the space telescope that I know Kuldeep might know a little bit more about the engineering there. Unfortunately, it's been delayed. We're hoping to send it up, I think, in the next 2 years. That's going to be the next game-changing telescope for astronomy, because it'll do something called spectra. It can take a spectra while a planet is transiting, and what we can do then is we can detect an atmosphere of an exoplanet. Once we can do that, that's going to be a real game changer, because we can detect, hopefully, something like water molecules or other molecules in the atmospheres of these planets that can give us a clue as to, eventually, if we detect enough of these, we can say, well, how frequent does water occur on other exoplanets? How frequent is there a layer of gas around a rocky planet that we think has the same kind of molecular composition that's friendly to life that we can think of? A couple years out, but we're already preparing for that. For the James Webb Space Telescope, we're already preparing to be able to detect those planets and detect atmospheres around exoplanets. It's sort of the next big ball game.
That's definitely a game changer right there.
I've always wondered, like, when you have like a different size planet at a different distance from a different size star, like, how does that all factor in? Is the presence of water and like a suitable atmosphere, are those, it's like, are there any properties that might, other than those, like the atmosphere and water, are there other properties that might vary as a function of like the planet size and distance away from its star, and the light that it emits? Like, there's a lot of,
You've shot the arrow right on the dot of what the problem is right now. There are so many variables that have made life on this planet possible. We can't even count. Here are the general ones that you've highlighted. One of them would be the size of the star. You guys might remember a couple of years ago, there was a detection of multiple planets that possibly have water around a star called TRAPPIST. Have you guys heard of the TRAPPIST system?
I have not.
It's an M dwarf star, so it's the smallest kind of star in the universe. And then in the universe, actually, the smallest type of star, these M dwarfs, are the most common. About 70%, something like 60 or 70%, according to theory, of stars in the universe are M dwarfs. So for a long time, we were always thinking, like, hey, if there are planets that are within the Goldilocks zone where we can have liquid water, if they're rocky, like here on Earth, that sounds like a great place for life to occur. There's a couple problems. One is if it's in the habitable zone of a M dwarf star, it's going to be so close to the star because when a star is smaller, it's generally much cooler. So it has to be really close in order to have the same temperature as a temperature like here on Earth. It'd have to be so close that the planet would be tidally locked. What that means is, because of gravity, as it's orbiting around its parent star, the planet will always have the same side facing the sun. On Earth, we obviously rotate on our axis every day, so we have day and night. On these exoplanets that we're finding around M dwarf stars, they're so close that they will only have one side of the planet that has permanent day and one side that has permanent night. So there's going to be a problem with temperature. It's going to be one side's going to be really hot, one side's going to be really cool. You might ask yourself, well, what about right at the boundary where there's day and night? Maybe that's going to be the perfect area to have life. Maybe. There's a second problem. These M dwarf stars, they're susceptible to flaring. You might have heard of something called solar flares that we're always worried about in a lot of apocalyptic movies. A solar flare will knock out power on Earth and things like that. It could actually be much more drastic. If you're close enough to a solar flare, it can incinerate your atmosphere. It could be so hot that it could literally, it would be like a hell scenario. And because these M dwarfs are really violent, they have a lot of flaring activity. That's that makes us question, like, maybe life really can't occur. It's going to be really challenging for life to occur there because it's not stable enough. There's going to be wild events that would throw things off course. I'll give you one other problem with interesting things that might happen in the system: the presence of other planets. Jupiter, which is the biggest gas giant in our own solar system, it's protected us from a number of asteroid collisions because of its gravitational influence. It's done a really good job. Same thing with the moon in shielding us from bombarding asteroids early on and even in the middle and later stages of our solar system to even now, protected us from collisions with asteroids that would be devastating to life on Earth, just like it was devastating to the dinosaurs 65 million years ago. You'd need all sorts of these perfect conditions to protect a planet from events that could really be a death knell, a nail in the coffin for life. So it's a complicated question. It's something we're really excited, and I think in the next 10, 15 years, we're going to have a lot more answers for a lot of those questions you asked, Peter.
Based on Peter's question, that reminds me of something I learned in space systems engineering, is that horizon sensors and satellites within the solar system, they use Earth's CO2 in the atmosphere and other gaseous materials to orient themselves because there's a very unique imprint in our atmosphere. So the satellites sensors will look at those and then orient themselves based on what the requirements are. So that was just going back to Peter's question on what else are people looking for with the habitable planets.
And, Colby, I'm willing to bet that some of the probably similar technology that we use to detect, that we're hoping to detect atmospheres around exoplanets for it. Is it spectroscopic? I'm sure. Is that how they detect?
Horizon sensors and sun sensors. Well, there's like a hierarchy. Horizon sensors are kind of coarse. Sun sensors are a little bit more accurate. And then star trackers are actually the most accurate and expensive things to put on satellites. But they work because they know all the constellations and stuff. So horizon sensors are like secondary or tertiary backup sensors, but the main ones will go off of the star trackers.
That's really cool. Wow.
So it's definitely not the spectra or like anything that specific, but it's the same concept that you're looking for something in the atmosphere.
Yeah.
So if you had to assign a probability in your opinion, just based on like the fact that we found 4,000 exoplanets in our galaxy, there's like 100 billion galaxies or whatever. So who knows how many potentially habitable planets there are. Obviously, though, it's still, we don't really know, for sure. Of course, there's no way to estimate, or there's only estimations that we can make on if there's life. But would you think that, because since obviously you're in the field, do you feel like there's definitely life on other planets if you had to make your guess?
I'd be willing to bet, well, I guess in cosmological sense, money doesn't really matter. I'm almost sure that there's life elsewhere in the universe. I think the really sad part when you think about astronomy is that one of the main modes for us to communicate is things like light. And light on a cosmic scale travels really slowly. And what that means is probably in our lifetime, I'm not gonna see evidence of life on other planets. There's I'll give you one thing that might be an awesome sign that there is life on other planets is that things like when we detect CO2 or oxygen around a terrestrial planet, hopefully with things like James Webb, around an exoplanet, that might be a really, really good evidence of life on other planets because in our own home, it's life that generates that kind of that signature. It's life that trees that produce oxygen for us to breathe. So if we detect that around an exoplanet, that's actually probably a good sign that there's something really interesting happening there. I'd say in my lifetime, that'd probably be the closest that we'd have to detecting life. Other than that, I'm so sure that there's definitely life elsewhere in the universe.
Yeah. And maybe another closing question, like for just general curiosity and like to, I don't know, kind of like a wow factor. But like, how big is our universe in light years? Like, is it in if you had to like, can you model the universe as a 3-dimensional immense cube? And like
that's literally how we run simulations of the universe. There's several simulations that.
Isn't there a thing called like the red something that's like at the edge of the universe?
In astronomy, we measure distances. Sometimes we measure distances. Actually, astronomers we don't even talk about light years as sort of a public-facing metric of distance. If I think about how many size of the universe, I'm just going to Google this because I don't know off the top of my head how big the universe is. How big is our universe? Blah, blah, blah.
Redshift. That's what it is.
Redshift. Yeah. So, this is a rabbit hole question for me because I'm gonna explain how we can determine. I think it's several billion light years ago. No, trillions of light years. How many light years is the universe? Observable universe. It's something like 3.4 billion light years. 3.4 trillion light years across, according to Wikipedia. But again, that's the observable universe.
And it's increasing exponentially as we speak.
That's literally like asking how many joules of heat are in the universe. So you're just taking an arbitrary thing that we understand and you're just applying it to the universe, but we won't ever actually know the answer to that. You're just taking a metric and like asking, you know what I mean?
Yeah. So so I can only say things about the observable universe. So the most distant galaxies would be something over 1 trillion light years away, which is huge.
It's huge, yeah. So like as a human being, we constitute probably a fraction of the fraction of all total space. If you think about that. So next time you think about your problems that you have, just remember how small you are.
That's right. And you can also do the exact opposite if you want to feel good about yourself. Where you say, again, for our knowledge, from what we know so far, life is super rare, super, super, super rare. I mean, it's hard to even, just as how small we are, is sort of the probability that life exists. There's probably, again, super rare. And in a way, I'm not sure who quoted this, but we're sort of a way for the universe to understand itself. I wish I knew who, because it's bad to cite. It's bad to quote things without citing
Google
it.
Google it.
So that sounds like a yogi quote or something. Yeah.
That does sound like a yogi quote, to be honest.
Yeah.
But it does sound like a Carl Sagan quote too.
It does sound Carl Sagan.
Yeah.
Yep, that's a quote from Carl Sagan.
There we go. What's up?
Should I say it start to finish so you can edit it out later?
No, it's okay. We can leave little discussions like this in there so it's fun for the audience.
Sure. All right.
You hear that, guys? We care about you. Like, share, subscribe. Yeah, but Peter, did you have any other closing questions? Or
I think it's a good place to end it off. Yeah, no, thanks for coming on, Jay. I think astronomy is a fascinating topic. We all want to know more about kind of where we stand in the universe, and I think like some of what we talked about obviously just scratches the surface, but I think it was really cool. And hopefully the audience, you guys can take away something of value. And yeah, Jay, best of luck to you in your endeavors.
Thank you so much, both to you, Peter and Kuldeep. It was a lot of fun to join you tonight and talk a little bit about something that I do. Hopefully, it gets people's minds off of some of the stuff that's happening in the world. It's a little bit not as interesting, or definitely interesting, not as happy though.
Absolutely. And if you guys have any questions about the material we covered in the podcast or just for Jay itself, you can email us at therootmotivepodcast@gmail.com and we'll pass it along to Jay.